Logistic regression is one of the most poorly named methods in all of statistics. If you call something regression, you would expect it to be doing regression. But logistic regression is doing classification. Classification. Naming it logistic regression is like naming your cat Fido the dog. That would be one confused cat. Nonetheless, logistic regression, we'll call it logistic regression because that's what everybody calls it. Nonetheless, it is a very widely used model, especially in medicine and for biostatistics and social sciences. Logistic regression is a good method. It can give you quite good performance. And so and the other thing which is nice about logistic regression is that it builds a foundation for some more complex methods like neural networks. And there's also generalizations called generalized linear models. So in this video, we're going to look at a sort of some intuitive motivation for the logistic regression model, how to think about it and what it's doing, and talk about some pros and cons. And in the next video, we will, well, hopefully I can get it in, and then by the next video, we'll start the formalism of logistic regression, and we will look at how to find maximum likelihood estimates using Newton's method. Okay, so let's look at a motivating example here. Example. Let's suppose you are an actuary. So suppose you are an actuary. An actuary is somebody, a statistician usually, who tries to figure out how long people are going to live and things like that for insurance companies and finance companies, and to basically make probabilistic models so that financial investment companies like insurance companies and so on and so forth can make more sort of informed decisions and make more money. So suppose you are an actuary and you want to build a model of how long people are going to, what is the probability that a person will die in the next 10 years. So you want to model probability. So you want to model P death given some data about the person. So this is a very happy example. And let's say that the variables, this x, is telling you three things. Let's say that x1 is the age of a person. Let's say that x2 is whether they are male or female. I will just put M or F. And x3, let's say, is the cholesterol level of the person. That should be a good indicator. Cholesterol. And you want to find a very, very simple model. So you have this data and you want to find a super, super simple model. And you want to have as few parameters as possible. So you say to yourself, well, let's see. What if I took a linear combination of these? What if I took, say, some offset W0 plus W1 times X1 plus W2 X2 plus W3 X3. So, and you say, well, let's see, when age is large, this is, and say this W is positive, then this thing is going to be getting bigger. So as the person is getting older, then this is sort of, maybe this is sort of something like it's more probable that they're going to die in the next 10 years. And also the cholesterol, if this W3 is positive, then as the cholesterol gets higher, then this term is making it larger. And this term, if maybe male is like, say 0 and female is 1, then this could give you some offset, either way to tell you, to sort of increase the probability or decrease the probability depending on whether the person is male or female. And so we can write this as a vector, W transpose X, where X is 1, X1, X2, and X3. So this is a standard convention to put the first coordinate to always be 1 so that you can have this nice linear combination here, and you get an offset term as well. So there's one problem with this, right? This isn't a probability. We wanted to get the probability. We wanted to model the probability, and this thing is just some, you know, some plane. So this is not a probability. And but you say to yourself, well, I can fix that. I can just send it through a sigmoid type of curve. So I can send it through a curve that looks something like this. So this is the origin. This is my, well, not x. I guess this would be like a, some a, axis, and this would be some function. Let's call it sigma of a for sigmoid. A sigmoid function is just a generic name. So sigmoid is a generic term for an S-shaped curve. So this would be 1 here, 1/2, say, something like that. So when this thing, so then we could pass this through a sigmoid function like this. So we could consider, let's put it over here, sigma of this dot product, and that would always be between 0 and 1. So that would be good. So maybe we should do this. So maybe we should do, the model is P def given x is sigma of W transpose x. And this is the model for linear, not for linear, for logistic regression. This is, I mean, you're not always modeling def, but this is the form of the linear regression. Linear, I keep saying linear. The logistic regression model is you model probabilities in this way. And this is, we're only going to talk about binary classification here. You can extend logistic regression to multi-class classification in a very natural way. But at least in these videos for now, we're only going to talk about binary classification. So this is the binary classification logistic regression model. Well, and I have to tell you what sigma is. So sigma here, what is sigma? There is a standard choice of sigma. Sigma A is what's called the logistic function, and hence the name logistic regression. Sigma is 1 over 1 plus e to the minus a. So we should include that in our definition here. 1 over 1 plus e to the minus a. This is called the logistic function. Logistic function. And let's try to draw a picture of what's going on here to just solidify our intuition for what these probabilities actually look like. So let's draw a picture. Let's draw down here maybe. Let's keep that. No, okay, that's fine. So let's say we have, so in our model here, let's think back up to this problem here. Let's suppose that x2 is 0. We fix x2 to be 0. We're going to look at just the x1 and x3 coordinates, age and cholesterol. And let's say for now, maybe w0 is also equal to 0. So what is this doing? Well, first let's think about this linear function here. So let's say w1 is, if this is the w1 axis and this is w3, maybe w1 is like 1 or something, and w3 is say 2. So this is a vector. If we just look at these two dimensions, w1 and w3 form this vector here. And so the level sets of this thing, W transpose X, when x2 is 0 and w0 is 0, we're just looking at this part. The level sets of this thing are orthogonal to this vector. So this is W, and the level sets are, let's see, this will test my drawing skills here. Level sets are these lines like this. And they're increasing in this direction. They're increasing as you go in the direction of W. So it's a sort of a plane sort of coming out of it's going through, through the page at this line right here that goes through the origin. It's going through the page because when x is 0, so like if this is, so if x is 0, if it's the origin, then of course w transpose x is 0. And if x is somewhere over here, or maybe say it's on the line w, or maybe it's actually equal to w, then this is w transpose w, and so that's going to be positive. It's going to be bigger than 0. And then when it's minus w, then you're going to have minus w transpose w, so it's going to be negative. And in general, when you're on this side, when you're on the right side here, it's going to be positive, and when you're down here, it's going to be negative over on this side. So let's draw that now. Let's see if we can, this will really test my drawing skills. So if we can, so first let's say, maybe we don't want, no, okay, that's fine. So let's try to draw that now in 3 dimensions, just to really make it drive the point home. So let me draw maybe a square here. So this will be like a square. And I'm going to try to draw sort of 3 dimensions. So if this is going to be coming out of the page, sort of. After you pass this, so what we're going to try to draw is after you pass this thing through this sigmoid function. Remember, this is the sigmoid function. This is the logistic function here. And we had a plane here, right? The yellow lines were this plane, this w transpose x. And after you pass it through this sigmoid, it's going to be sort of, small. It's going to be getting close to 0 down here. And then it's going to increase, and then it's going to be going through a half right at this point. This is sort of, I'm drawing a line coming out of the page. And then it's going to be getting closer to 1 as x gets bigger. So let me try to draw that, what I was doing here in 3 dimensions. So this is sort of coming out of the page, when you're up at this corner, you're going to be close to 1. This is going to be the origin. And then if we were to trace the line as x goes along this line right here, this function, sigma, the probability, remember this is the probability, this is going to be sort of hovering above the page here. This vertical axis is this p. And then it's going to go down, it's going to hit a half when it's at the origin, and then it's going to get small down here. Let me try that again a little bit. Try to clean that up a little bit. So it's something like this. And more generally, it's going to look something like this. So up in this area, it's going to be high, and then it's going to sort of drop down. So you're going to have this sort of region here. Hopefully this sort of is helping you to visualize what this looks like. So it's this sort of, this function in 3 dimensions, kind of, it starts out small down here. It's very small, near 0. And then it climbs up. It hits a half at this line here. And then it gets closer and closer to 1 as x is getting larger in the direction of w. And so this is what the probabilities are looking like. So if your age, and cholesterol level were at this point here, if they were pretty big, then you're going to have a high probability of death. Whereas if your age and cholesterol level were down here somewhere, then it's going to be lower. And so the offset then, if W0 is offset, then you can shift this whole thing like a wave. Like a wave, it'll be shifted in that direction. Okay, so hopefully that gives you a sense of sort of what these surfaces look like. And next we'll formalize this.